Okay, given the objective of the requirement and also the principle of the constraint, we need to come out with a solution for connectivity, scalability, and resource sharing. And we need to talk about how Internet make its decision on this, and then the actual control plane and data plane operations. And before that, I'd like to before talking about the solutions of the Internet, I'd like to review what other solution we have. Well, Internet is just one solution, which is the bottom one, the IP, the stateless routing, the IP protocol, stateless routing. And what are the other solutions? Well, from the hot state switching, which is the plain old telephone system, to ATM, which we have discussed, and then to MPLS, which try to switch, if possible. If not possible to switch, then routing. Okay, so let's start from POTS, plain old telephone system, where it's circuit switched, not packet switched, and it dedicates resource to a particular call. So when you want to make a phone call, you need to do the call setup, and it's circuit switched. It would allocate a resource to that particular call in a node and also in a link. In a link, it would allocate a bandwidth for that particular call, and in the node, there'll be a table entry, in a circuit table entry established for that call. And then along the path, it's all reserved. Okay, all established. The resources have been established during the call setup. And once done, then you start to talk. Okay, that's parts, plain old telephone system. How about ATM? ATM is not circuit switching, it's packet switching. So, however, it still needs to set up the connection first. So you still need to do the connection setup. But now, you don't actually do the circuit switching reservation on the bandwidth. You still have table entry in the node. And for the link, you allocate bandwidth mostly statistically instead of fixed partition. You don't partition the bandwidth to that particular connection. You still share with other connections. And however, I do the calculation to say, okay, you are okay to come in, and I have considered your bandwidth requirement, and I let you in. So you do that kind of soft reservation. However, the reservation on the bandwidth and also on the node, the table, is hot state. Meaning, here the hot state means that the allocation or the establishment for this particular connection will be there until you tear it down, until you tear down the connection. Otherwise, you'll be there. You'll be there. So after you set up the connection, then you start to send the data or the voice, okay? And then once done, the transmission is done, then you tear down the connection. That's when you release the resource. You release the resource. So it's called hot state. How about soft state? The MPLS. MPLS says, okay, it's still packet switching. However, I don't want to do a connection setup for all the connections. Okay. If a packet comes in, and then at first it'll be routed. say a packet. If you want to set up, you want to transmit, then you just transmit, okay, and the packet will be routed, okay. However, if the packet stream is a persistent flow that that might have a lot of packets to transmit along the path, then I might decide to turn the routed stream into a switched stream. Meaning I would try to tell the upstream, okay, give the label to the upstream saying, okay, for the subsequent packet, please label the subsequent packet with this label. And then if you label this, then I would know, because I have set up in my table for this label in my switching table. So if the subsequent packet with this label comes in, I will look up this table and find, okay, these are label packet, and with this label I should switch to that particular pole. Then I turn a subsequent packet into the switched mode instead of routed mode. So if I have, say, 1,000 packets traveling along the path, okay, passing through MPLS switch, then what happened is that the first few packets, say the first 10 packets, might be routed. Then from packet 11 to packet 1,000, it will be switched. So the first few will be routed, but the others will be switched. Then it's called route once, switch many. Route once, switch many, meaning that I route the first few, or the first packet, or the first few packets, which is slower. But later on, I decided they need to be, they will persist, and I should turn them into the switching mode. So I established the table entry for them, and I notify the upstream, asking the upstream switch to label the packets, to label the subsequent packets, so that once I receive them, I can switch for them. So these are called the route one switch many. So MPLS, the beauty of MPLS is that it combines the routing and switching. I can do both. However, I keep the table entry for that particular stream, but that state kept in the table might expire. It would expire. So after you finish the packet 1,000, after you finish the packet 1,000, then if there are no more packet, no 1,001 packet coming in for a long time, then the state information in the table will expire. So then I would forget about the state. A strong need for signaling protocol to do the connection setup. Okay, so that's the beauty of MPLS. And that's called soft state switching. And of course, we have mentioned that IP, the internet, is the static routing. Let me give you an example. Then you will immediately see the difference. So the hot state switching is like a marriage. The marriage, where in a marriage, when you are married with a person, then you are married, unless you two sign the divorce agreement, right? And so that marriage is hot state, right? It would not expire automatically. Okay, even if you don't live together, say you marry, but you travel to some other place and you are separate for 3 years, is your marriage still effective? Yes, it's still effective. So it's hot state. However, if you are friends, the girlfriend, boyfriend, then it's soft state. There's no agreement, there's no contract. And if I don't date you, for 3 months, that means it expired. Right? So that's soft state. It would expire. And you need to refresh periodically. If you don't refresh, if you don't call, if you don't date, then it will expire automatically, which is good for some people, but bad for some others. Okay. And stateless routing is like strangers, or I don't, well, it might not be that appropriate to talk in the class. It's like one night stand, that you are strangers and you treat every packet independently, no engagement, no state kept. Okay, so that will be give you a clear idea about how they differentiate from each other. So this is a spectrum of statefulness, where you have stateful, the most stateful network, which is the telephone system, the traditional telephone system, and then you have ATM, and then others, which is also connection oriented, and then MPLS is a combination of connection oriented and connectionless. So you can do routing and also switching, and it's route one, switch many. Mostly I do routing, but for some flows that would persist, that would need faster handling, I do switching. Okay, so it's a combination of routing and switching. But here you do routing. Okay, and for MPLS, it's embedded in the internet, but not in a large scope. So say some ISP, some internet service provider would have their backbone turned into MPLS. And it's only within their service domain, but not cross different ISP. Okay. Okay, I was saying some ISP try to adopt MPLS to a limited scale at their backbone, but it's only within an ISP, but it's not across multiple ISPs. Say it's possible that if my packet needs to travel from, say, Taiwan to Europe, and say 15 hubs across, say, 4 ISP, for example. So 15 hubs through 15 routers, and I need to pass across 4 ISP. Perhaps one of the ISP has introduced MPLS. So, but it probably account for 4 hubs within those 15 hubs. And within those 4 hubs, they probably use MPLS to help to speed up the backbone. Then my packet might be switched within those 4 hubs, which is faster. But for the other hubs, they will be routed. So it's possible. And some ISP has deployed MPLS to speed up their own backbone. Yeah, but it's difficult to deploy MPLS across different ISP. Okay, so let's see. So having this in mind, you know where we are and where differentiate the others. We'll solve the problem of connectivity, scalability, and resource sharing in different ways. Okay, but their features, their philosophy, design philosophy is different from the internet or the IP. And what is the philosophy behind the internet architecture? Okay, so let's look at the solution to connectivity. It says that it's a routed connectivity maintained at end-to-end. So it's not switch connectivity, is routing connectivity maintained at end-to-end. And here the end-to-end means that the end-to-end argument. So routing connectivity means stateless and connectionless. You don't want to keep the state in the core of the internet, and it will have low overhead for the bursty, long-lived, or short-lived connectivity. So if there are some flows in the internet which are short-lived, very short-lived, say just a few packets, and then done, then it doesn't make sense. It doesn't make much sense to establish connection and state for those short-lived connectivity connections, for those short-lived connections. So having a stateless core, stateless connectionless core, means low overhead. While if this is a stateful and connection oriented, it means that you still need to set up a connection, even if you just want to send one packet, one data packet or 3 data packets. Then you still need to set up a connection first before you can send the packet. So the overhead will be then high for those short-lived connections. Okay, the other, it says that this routing connectivity is maintained at end-to-end. The philosophy behind is the so-called the end-to-end argument. The end-to-end argument. The end-to-end argument says that you want to do the end-to-end instead of hub-by-hub mechanism. And it says that don't put it in a lower layer if it cannot be completely done there. Or don't put it in the core of the internet if it cannot be completely done there. Then the end result will be that you push the complexity to the edge of the internet while keeping the core simple as possible and stateless. Okay, so that's the end-to-end argument. So by saying don't put it in the core, it's similar to don't put it in a lower layer unless it can be completely done there. And it says that so the compressor will be the end-to-end, the edge, and the core will be simple. However, you still put some in the core only for performance optimization. And error control is one example, one typical example for this. Say, I cannot guarantee my error control is perfect. So if I put the error control at hub by hub, I still might have error end-to-end. Why? Because when we do the error control hub by hub, okay, I say I'm transmitting to you, okay, and I make sure my transmission on the link is error-free. Okay, if there's an error, you will detect, and I will know that, you will tell me, and I will retransmit. Okay, fine. And if everybody do this, so we make sure that the transmission on the links are error-free or can detect and correct the error. Then can we guarantee the path is error-free? Can we? No. The reason is because this link is error-free and that link is error-free, but there could be error on you because of what? The nodal error. What is a nodal error? The, say, memory error. We just mentioned, we just see that there could be error on the router, in the router memory. What written in could be different from what read out, right? So because of the memory error, the nodal error, possible nodal error, so even we make sure that the links are error-free, we still cannot guarantee the path free, right? So doing link error control at the link level or the hub by hub level is not enough to guarantee the end-to-end free, error-free, right? So we still need the end-to-end error control. However, can we remove the error control at the link layer? Okay, can we do that and just do error control at the end-to-end, at the end host? Can we do that? Yes, we can, but the problem is that the error will be detected late and recover late, right? So I have from the end-to-end, I have put error control at the upper layer, but at the link layer, I don't do error control. So if there is something wrong, some error hit the packet, and it traverses to the destination host, and eventually the destination host will detect the error, and then notify the source, and then source will retransmit, for example. Then the time it takes to detect and correct the error will be long. So what we want to do is that we want to do the error control at the link layer and also at end-to-end. And the reason for putting at the link layer is for performance optimization. We want to detect and correct earlier, and this is important, especially when you have more link error or more nodal error. Okay, and then you would detect and correct early enough to correct them. Otherwise, you'll be too late. I mean, quite late to detect and correct. But even if we do the link layer error control, can we forget about the end-to-end error control? No, I just say that we still need end-to-end in order to protect the data from the nodal error. Okay. But given this end-to-end argument, that will push the complexity to the edge, and the connectivity, the routing connectivity, are mostly maintained end-to-end, even though the hub by hub or the link layer could help a little bit. And then this connectivity, since we have mentioned that you would have edge and link, edge and core. So you would need to break down the protocol into hierarchy. And for handling the link layer issue or the upper host to host issue or the process to process issue. So eventually it grows into a 4-layer protocol stack for the internet. That the first layer, the link layer, will be covering the physical and data link sublayer, or sometimes we call it 1 layer or 2 layer. So physical, PHY stands for link layer. And mostly it's implemented, as you will see, that it's implemented in the hardware mostly. And then the IP layer, which deal with the host to host, okay, or node to node layer. And then you would have process to process, because at the end host there could be multiple processes. There could be multiple processes listening on some port numbers. So then you need another layer to support them. So then you have TCP layer and UDP layer at the transport layer. And then the application layer, client server application or peer-to-peer applications. So one possible example will be you would have Ethernet header encapsulating IP header, encapsulating TCP header, and then encapsulating HTTP header, and then encapsulating the HTTP payload. So there'll be something, a protocol stack like this, that here it's the IP layer at the core and transport layer, 2 possible choices, and then on top you have applications. And then at the bottom you have different links different physical layer and link layer, data link layer. So it's the protocol stack of the internet is like an hourglass. That you have one single protocol, which is IP in the network layer, and multiple on the physical and link layer, and then many on the applications. And the one I put into the red font, these are the red with red font and dotted circle. These are the control protocols, while the one in black are data protocols. And with the protocol stack, naturally you want to send the data, which is the payload, and then it needs to be encapsulated by different protocol headers. Say if this is an HTTP web application, then you would have HTTP header and then TCP, IP, and Ethernet or wireless LAN. So you would so when you transmit from the application, it is a process of encapsulation, and when you receive a packet from the link layer, and then it's a process of decapsulation and encapsulation. How about a solution to scalability that you want to have a three-level hierarchy that will scale to billions of hosts, and then the solution will be just 3 level, and you would have the group. The group is so-called the subnet. You would have subnet, and then on top you would have autonomous system or domain. Autonomous system or domain form the internet, and a subnet by definition is a network with contiguous address block, meaning that they are, if the hosts are within the same subnet, then they would have contiguous addresses which are nearby. So you would not have say address with the contiguous host with contiguous address within the same subnet, but they are located separately. No, they should be located in the same neighborhood. So that's the point. It's like you have a street address in a city, and it's a University Row, 1001 University Row, and you are looking for 1002 University Row, and it should be a neighbor of 1001, right? So it shouldn't be far apart. Otherwise, the address does not mean anything. So the address should mean something, that meaning the neighborhood. It would imply the location. So the IP address does imply the location, and actually you can have a map of IP addresses with given an IP address, you could tell there's a service, IP mapping service. You can tell where this address is, in which country, in which city. Okay. So that's a subnet, and then you need and the subnet. The network address is designed as 32 bit. then you need a NAND mask to tell within those 32 bits which part will be the network address and which part will be the host address. So you need a NAND mask to tell which part is the network address. And then those address, the network address within covered by the NAND mask is called the IP prefix. IP prefix. Okay. So if we take a look at the example here, and that's the address within NCTU, with the campus, and NCTU has been allocated with the address of 140.113, and within this, the network, the host address, the 16-bit host address is managed by NCTU, and totally there could be 65,000 addresses within NCTU, but within NCTU there are less than 20,000 machines, probably around 20,000 machines within NCTU. So only about 1/3 of the addresses have been used. So we got 65,000 and less than 20,000 are used. So like 35% of the address space has been used. And worldwide, probably this number is good enough worldwide. Because the reason why it's not the utilization couldn't be better is because the way we allocate addresses. Okay, the way we allocate addresses is that I give you a block, and then it's up to you to use, and then probably utilization is 30%, and this is utilization is 40%. And because the address has been allocated, I have no management. I cannot control the management of these addresses. Okay, then you will see that the NAND mask for this address space, that is 65,000 entries. Within this space, the subnet will be 140.113. That's NCTU, and with a NAND mask of 255.255. That's 01. So these 16 bits are 01. Okay, and that's the NAND mask. And if you take this and this AND together, if you AND these two streams together, then you will get the network address, which is 140.113. And then you could have a divider within this space. Within this space, you could divide it into multiple subnets. Say I divide this each segment of 256 entries will form a subnet. So I have a subnet of this with a NAND mask of this. So the network address is 140.113.255 with a NAND mask of this. So I can break down into a subnet, which is called subnetting. And if I do this, I have a network address of this, and this network address is also called the IP prefix. So I have a prefix of this. And that's with netting. I can divide into multiple subnets. And actually, NCTU does this subnetting by this. See, how many? If each subnet is 256 in size, 256 addresses in each subnet, and I could have 256 subnets, right, at NCTU. So I have 256 subnets within NCTU, and each of the subnet is 256 in size. And then the computer science department said that I need 16 subnet. Each will be 256 addresses. And I have this. So the address, network address of this, from this and to this, totally 16 allocated to the computer science department. And the EE department says that it needs 8 subnets. Each of them will be 256 in size. And mechanical engineering says I need 4 subnets. So I got 256 subnets, and I allocate probably over a half subnet to the department, and some to the administration offices, and some to the dormitories. So and then NCTU itself is a domain, or called autonomous system, which is big enough. And how many totally on internet have? How many domains do we have on the internet? There are around 60,000 domains on the entire internet. Okay, so on top, there could be multiple domain or autonomous system, and within the autonomous system there could be many subnets. So you got the problem of intra-domain problem and inter-domain problem. Intra-domain and inter-domain problem. Within the domain, the problem size is not big. Say within NCTU, how many subnets do we have? 256, right? So the problem size is 256 for what? For NCTU backbone routers. For NCTU backbone router, it handles 256 subnets. Okay, so the problem size is hundreds. However, so the intra-domain problem size is usually hundreds, but in the inter-domain, tens of thousands, right? So the problem size becomes tens of thousands. Inter-domain problem size is big, and so when we are doing routing for the inter-domain routing, some of the NCTU backbone, 1 or 2 NCTU backbone will participate the inter-domain routing. And then that router would need to handle tens of thousands of network. Okay, so that the problem size is much bigger. So consider this, if we are talking about, say, 50 million hosts and 1 million routers today, for example, and then the subnet size is 50, and the number of subnet in a domain will be is also 50. Then and we have 20,000 domains. Then you could you would have the inter-domain router would need to handle a network size of 20,000. However, the intra-domain router only need to handle the problem size of 50. Okay, so you will see that in for a problem size of tens or hundreds, the solution you need will be different from the solution for a problem size of thousands or tens of thousands, right? Okay, so we will see that why the Dijkstra algorithm cannot scale to the inter-domain routing. Why? Because for the Dijkstra, you need what? The entire topology. So if you have an entire topology with 1,000 or tens of thousands router within this topology, then it would take too long to do the shortest path calculation. So the diaspora cannot scale to this size. So for this, you need Bellman-4 algorithm, which is more scalable and that can scale to this size. So when we talk about the scalability issue, we can easily break down the internet into three-level hierarchy. However, at different layer within the domain and between domains, the problem size has a big difference. And usually it will require different solutions to solve these two problems. You can apply the same solution to these two problem size. Okay, and the solution to resource sharing is that it says that we want to have common best effort service, where the best effort service here means I try my best, but it doesn't mean the service is best. It means I will try my best. So the service would not be best. Okay, that's how you interpret best effort. Okay, so it's unreliable IP because why it's unreliable? It does not have connection set up. It does not maintain the state. And so you cannot make sure that the packet will get through. The packet might be dropped. So it's unreliable IP service in terms of throughput, latency, jitter, and loss. So I cannot guarantee the throughput. I cannot guarantee the latency and jitter. I cannot guarantee even the loss. Meaning that I cannot guarantee that this packet will get there. It might not get there. Okay. So that's the so-called best effort service provided by IP. Okay. When it's lost, it's lost. I don't try to recover it. I don't try to recover it. If I do the and then it's up to the upper layer. It's up to the upper layer to, if needed, to recover the packets. So at the end-to-end layer, because of the application, some of the applications need reliability, some applications don't. Then what we should do is that we provide two kind of end-to-end service. One is the reliable TCP in terms of loss. It will guarantee it will get there. Reliable TCP and unreliable UDP. So you have two protocol choices at a transport layer. One reliable and one unreliable. So UDP just both right on top of IP layer. Both of them. And for TCP, it provides the reliability. It makes sure that the packet will get there by acknowledgement mechanism, by retransmission, by sequence number. So by this kind of mechanism, it would make sure that the packet will get there. However, UDP does not. It is still connectionless. Okay. So it has no way to provide the reliability. Then you might ask, how the TCP, in order to guarantee the reliability, TCP is connection oriented, while UDP is connectionless. Then you say, okay, are we talking about the IP is connectionless, but how come TCP is connection oriented? Okay, the connection of TCP or the end host, say I have host A, host B, and in the middle is internet backbone across many routers. Then the router does not implement TCP or UDP layers. It only implements IP layer. And so I have a TCP source here and destination here. And in order to provide reliability, they set up a connection and keep the connection state at the end host. However, the connection or the connection state are not kept, not aware at the routers. The routers in the backbone are not aware of the connections. What they see is that they only see IP packets. They don't see the TCP connections in the routers. Okay, so even if you are running on top of connectionless IP backbone, you still can have reliable TCP and connection setup. And that connection is only maintained at the end host, not at the routers. So the routers is not aware of the connection and still kept connectionless and stateless. So I don't know whether this is clear to you, clear enough to you that the TCP connections are not aware, are not kept or not kept in the routers, and the router are not aware of these connections or these connection states, and they are only kept at the end host, and it's the end host that maintain the reliability, doing the connection setup and maintain the reliability, doing the acknowledgement, doing the checksum, doing the acknowledgement, doing the retransmission, all done by the end host. It's not relevant to the routers. So that's called the end-to-end services. And also for resource sharing purpose, well, you need to share the bandwidth. So you need to do congestion control or flow control. You need to do congestion control and flow control at end-to-end. So TCP exercise a window-based control mechanism, okay, to limit the number of bytes or the number of packets that can be running or in transit in the internet. So if I have a window size, okay, of 100, it means that I can only have at most 100 packets in transit, unacknowledged in transit, meaning I'm contributing 100 packets on the internet, but it's limited. It cannot go beyond 100. So doing that will reframe a TCP source from pumping too many packets on the internet. And if everyone do this and try to have a window size to limit their traffic contribution to the internet, then the chance for congestion will be lowered. So what it does is it provides better fairness. With this window control, have fairness, and then they would have approximately equal outstanding bit, which is decided by the bandwidth delay product for any flows. So everyone will be, well, I comparing different flows, you will see better fairness that where one single flow will be dominating the bandwidth. No, everyone will be reframed by the window size. And then you still need to adjust the window size, because with this window size, if you continue to use this window size, probably sometime the path is congested and you still pump so much, then it's not good. So if the path is congestion, you need to adjust the window size to be smaller. If the path is clear with abundant bandwidth, then you increase the window size. So you adjust the window size, adjust to reflect the network and receiver condition. And usually the adjustment of the window size is done by AIMD, which is called additive increase and multiplicative decrease. So when you increase, you don't want to increase that fast. But when you decrease, you want to cut into a half. What you do is you usually cut into a half. Okay. And so it's a dynamic window based flow control and congestion control. with this, then the internet will be kept healthy and less vulnerable to congestion. However, TCP does this, but UDP does not. It does not exercise congestion control, flow control. So TCP is you can say TCP source is a polite traffic source. However, UDP is a wild traffic source. It transmits whenever it wants. And so UDP, if you have a high percentage of UDP traffic on the internet, then the internet will become more vulnerable to congestion. Fortunately, the TCP traffic still dominates the internet. You might say, okay, I got streaming, but most of the data transfer are done by TCP for the purpose of reliability, and for UDP mostly for some purpose. For example, we see that UDP, some applications run on top of UDP, but they are either confined to local area, say network file system, which is quite local, and some are for peer-to-peer queries. Say, I send a lot of queries on the internet, but I do use writing on top of UDP. I send UDP packet for queries, but I use TCP to do the file transfer. Okay. And another example will be I use UDP for what? For voice over IP. Voice over IP. But for voice over IP, is the bandwidth big enough to dominate the internet? No. Now the voice codec could compress the voice traffic to 4 kb per second or 8 kb per second. So we are talking about very small bandwidth from voice over IP. How about streaming? Right now, if you view YouTube, is it on UDP or TCP? It's on TCP. It's on TCP. It's not on UDP. And so until now, the TCP traffic still dominates the internet, accounting for a higher percentage, much higher percentage compared to UDP. So the internet is still healthy. However, there are people concerned about UDP. If we got, say, voice over IP or teleconferencing and high quality teleconferencing on the internet, and they definitely need to run on top of UDP instead of TCP, because for those hot real-time application, voice over IP, teleconferencing, they need to run on top of UDP because they don't want retransmission, they don't want flow control, congestion control. So, and they don't want reliability. If lost, fine. So they write on top of UDP, and if those kind of traffic continue to grow, then the internet will be more vulnerable to congestion. So researchers are encouraging to exercise, to turn UDP into so-called TCP friendly. You need to be TCP friendly. I mean, for those UDP, so that if you got more UDP traffic, they don't, because they are wider, and they would overkill the TCP traffic. So consider on the street, in the transportation system, majority of people, say 70% of people, say 95% of people are polite, and they obey the traffic signs. However, 5% are not. They don't watch the traffic signs, so they just go as they want. Then it's probably okay because they are only 5%, right? But if that 5% continue to grow, say to 20%, then there'll be trouble. And who will suffer first? The majority, right? The TCP. So the TCP will suffer if you got more UDP. And so researchers are saying that if UDP are growing, then you need to impose some TCP-friendly congestion control so that they are TCP-friendly and would not cause trouble to TCP traffic. Okay, so we are talking about the resource, the way to share the bandwidth, the resource. And at the bottom, IP is the best effort service, no reliability, and because no state maintained at the core, at the router. However, you transport layer at the end host, you got two choices. And when you have two choices, you depending on the applications, it will make the TCP, the choice as TCP or UDP. And right now, fortunately, right now we are still, the traffic is still dominated by TCP. Okay, so we cover the solutions, the three solutions, and then we see what has been done at the control plane and the data plane. So the control plane, I just list the control plane operation at the routing, and indeed it's pre-computed, not on demand, and it's in the background, hub by hub routing instead of end-to-end routing, and it's per destination network, the granularity, and you got intra-domain and inter-domain routing. And intra-domain routing, you can use, because the problem size is small, so you can either use global information or the topology or the partial information from neighbors. But for inter-domain routing, because the problem size is too big, thousands or tens of thousands, so you can only rely on the partial information to do the computation. And it does compute the shortest path, and it maintains only the single path. And the error reporting is done by ICMP at the control plane. At each internet node, you need to implement ICMP, which says that if there is something wrong, I will send ICMP packet to the source of the packet, which is in trouble. If a packet is in trouble, then I send ICMP message to the source of that packet. And host configuration, which is done by DHCP. And then the data plane, which is called for the first basic example is forwarding. And it does the so-called longest prefix matching. Longest prefix matching, meaning it would check the prefix. However, if there are multiple matches in the routing table, you pick the longest match. So that's called the longest prefix matching. And the operation of longest prefix matching is explained in detail in chapter 4. And then error control, you do error control, but at the end-to-end and also at the link layer. So you have error control at the link layer for the purpose of efficiency, but it's still not enough. You need to have the end-to-end error control at a TCP or UDP. At the IP, they put extra error control at the IP layer. However, they remove it in a new version of IPv6. In IPv6, there's no checksum in the header, but in the IPv4, you got checksum. And then traffic control, which is end-to-end. We just mentioned that TCP does traffic control, but UDP does not. So there are ongoing talks on how to turn UDP into TCP friendly. So in summary, here's a sidebar talking about the flavors of the Internet architecture. So what's the flavor? It pushes the complexity toward the edge devices and keeping the core network stateless and simple, and only implement IP layer at the core up to the IP layer. And a simple 3-level hierarchy with subnet and domain will be enough to scale. And how about the possibility for a stateful core so that we can do switching? And the answer is, as I mentioned earlier today, by MPLS you can do that, but only at a limited scale within an ISP.